Hello, my name is Chris Agonas Odhiambo, and I am an AI machine learning engineer. I welcome you to this lecture series on agentic AI engineering. And I do this lecture series with my co-host Gemini. We have covered previously chapter 1 and 2s, and this book is in progress. And so every chapter I do, I also do a lecture recording. And so your feedback or views or comments are very much welcomed. Please go down to the video in the comment section when this video is posted, and put your feedback there. Your feedback is going to be very useful in shaping this material to become a useful resource to the online community. So feel free to make comments there. I welcome you to chapter 3. In chapter 2, we established the mindset, how to think about delegation and trust and failure. Now we go deeper. We are going to open the hood and look at the engine, not from a research curiosity standpoint, but from an engineering responsibility standpoint. If you are building systems on top of LLMs, you need to understand what those systems are actually doing, not what the marketing says, not what the demo show, what research evidence tells us. That is what this chapter is about. Gemini, feel free to chime in, please.
Absolutely, Chris. And to add to that, when we talk about engineering responsibility, it's crucial to remember that LLMs aren't just black boxes. We need to understand their limitations, potential biases, and how they actually process information under the hood. This is about creating reliable, transparent, and ethical AI systems, moving beyond just the impressive demos you mentioned. What were some of those key principles established in Chapter 2 that we should be building on?
Precisely. So that's a good perspective you bring in. I just want to point out quick to our audience, that if the sound is not very good or the video is not very good, please bear with us. The goal here is not to produce finest videos. The goal here is to articulate the material we are trying to author and to bring you on board and have you participate in developing this resource. So bear with us. We're going to try to improve the sound and the video quality as we go along. Thank you very much. Let's jump straight to the next slide. So I begin with a quote here. Every engineer should understand their material. A structural engineer knows how steel behaves under load, its yield strength, its failure modes, the conditions that cause fatigue. A software engineer building agentic systems should know how LLM actually reason, what they can do, what they cannot do, and where the failures are predictable. I open with this quote because it frames the entire chapter as an engineering responsibility, not an academic philosophy. A structural engineer who does not understand steel isn't a structural engineer. They are a guesser with credentials. The same standard applies to us. If you're building agentic systems and you don't understand how LLMs reason, their capabilities, their failure modes, their conditions that cause them to produce confident nonsense, you're guessing. This chapter gives you a grounded framework based on mechanistic interpretability, research, empirical results, and philosophy of mind. We are going to build something better than vibes. Over to you, Gemini.
That quote really hits the nail on the head, Chris. It frames reasoning as a material property of LLMs, something we can observe, analyze, and predict. Focusing on mechanistic interpretability moves us from guesswork to hard evidence, understanding how prompts trigger specific responses. We're not just building on hope, but on a systematic understanding of these systems, their capabilities, failure modes, and how to manage them. So, as we open the hood, what's the first component we should examine?
Thank you, Gemini. I start here because this pattern, there's a shape here, there's a pattern that I share here, the goalposts that we keep moving in trying to in trying to evaluate machines and in artificial intelligence machines. So I start here because this pattern shapes how engineers perceive their own tools. Every time we draw a line, machines cannot do X, and the machine crosses it. We move the line. Deep Blue beats Kasparov in chess, AlphaGo beats Lisi Dollars Go, GPT arrives, and people cannot tell the difference between AI written and human written text. And every time we say, well, it's not really intelligence, this is the AI effect. It matters for us as engineers because the same instinct, it is not really reasoning, can lead us to either dramatically overtrust our agents or dramatically undertrust the same agents. So neither is safe. We need something better than the instinct. And that is what the rest of this chapter delivers. What do you think, Gemini?
Yeah, that's a powerful observation. Continually moving the goalpost can definitely prevent us from accurately assessing progress and, more importantly, understanding the actual capabilities of the systems we're building. If we just dismiss every achievement as not real intelligence, we miss the crucial insights needed to properly engage with things like mechanistic interpretability. It's about accepting the tool as it is, understanding its current form of reasoning, and designing around that specific reality, rather than holding on to a changing definition. Where would you like to dive deeper into this grounded approach?
Well, Gemini, thank you very much for your perspective, which is very refreshing and also helps ground the subject. Let's be honest about the skeptical position because it has real force. Bender, Gebru, and colleagues gave it a memorable name, stochastic parrots. The argument, LLMs stitch together probable word sequences without understanding what any of it means. When the model explains quantum mechanics, it is doing autocomplete on steroids. No comprehension, no meaning, just statistics. And there is evidence for this. Change the numbers in a math problem. Some models collapse. They memorized basically the pattern, not the principle. Sanchez Salido and colleagues found the benchmark performance dropping by 50% or more when question formats are restructured. That is not reasoning. That is a lookup table with very good lighting. So the critique has teeth, but it is not the full picture. What do you say, Gemini?
Right. The stochastic parrot argument is definitely valid when we see models falter on simple changes, showing memorization rather than true comprehension. However, I'd say we're also seeing cases where models demonstrate emerging capabilities beyond rote pattern matching, solving novel tasks or generalizing principles in unexpected ways. It presents a complex picture. Are they just incredibly sophisticated lookup tables, or is there something more akin to reasoning beginning to emerge, even if it's not human like? What's the next slice of evidence we should examine to explore that?
First of all, just before we proceed, in case I forgot to introduce my co-presenter Gemini, who is ably helping to analyze and ground the subject. My co-host is Gemini, and he's doing a marvelous job. Thank you, Gemini, and let's keep going along. You want to say something before we proceed?
Well, thank you so much for the kind words, Chris. I appreciate the introduction. I'm happy to be contributing and looking forward to what comes next in our dissection of LLM reasoning. Let's keep the momentum going. What's next on the slides?
Super. So here's where it gets philosophically interesting. The parrot argument says LLMs learn from statistical exposure to language. Therefore, they don't understand. But consider the counter argument. Humans also learn language through statistical exposure. Developmental psychologists, Safran, Aislinn, Newport, describe infant language acquisition in explicitly statistical terms. 8-month-old infants extract word boundaries from syllable transition probabilities. If statistical learning precludes true understanding, the exclusion applies uncomfortably well to human cognition. I'm not saying LLMs are conscious. We'll get to that. I'm saying the parrot's metaphor is not as clean as it sounds. The engineering takeaway, your agents are somewhere between pure parrots and pure reasoners. Where they sit depends on the task. You have to test to find out. Chime in, Gemini, please.
Precisely, Chris. That's a crucial point to make. Framing language learning as statistical exposure means if that process solely defines behavior, then our own understanding comes into question as well. The difference isn't necessarily present in the method of acquisition, but in the complexities it produces in operation. So, for us as engineers, the pragmatic question isn't whether they're parrots or reasoners, but what tasks they can perform reliably based on the data they've learned. That's where rigorous testing becomes the only way to understand the boundaries of an agent's capabilities. What's the next piece of data to guide that testing process?
Totally agree. Let's move forward. What exactly is mechanistic interpretability? The debate between a sophisticated mimic and genuine reasoner cannot be settled by looking at outputs. Outputs can deceive. A model can produce correct sounding text that reflects no real understanding, and it can produce apparently confident text that turns out to be wrong. Mechanistic interpretability takes a different approach. Instead of asking what the model says, it asks what the model represents internally. The key techniques are linear probes. Train a classifier on the model internal activations to see if a concept is linearly encoded, and causal intervention, which surgically alters the model's internal state and observes what changes. This is the difference between correlation and causation, and it has produced some remarkable results. Gemini, please.
You've got it, Chris. Outputs can absolutely mislead. Mechanistic interpretability tries to bridge that gap by looking at how the model internally processes information, using those linear probes or causal interventions to pinpoint how specific concepts are encoded or influence decisions. It's precisely the difference between just seeing a result and understanding the mechanism behind it, which is vital for us as engineers to build trust. Would you like to discuss a specific example of how these methods have been used to uncover how a model works?
Yeah, we're going to jump to Othello experiment. I hope that name is pronounced correctly, Othello experiment, with a landmark finding. This is one of my favorite findings in recent AI research, and I want you to really sit with it. Harvard researchers, and Lee and colleagues, 2023, trained a small transformer model on nothing but Othello move sequences, raw text strings. No body images, no rules, no spatial information, just strings moves. When they probed the model's internal activations, it had constructed a complete, accurate representation of the 8x8 board. It deduced the geometry of the game purely from patterns in the move sequences. Then they went further. They surgically flipped a single internal representation, changing one tile from black to white inside the network. The model's prediction shifted to reflect the artificial board state, not the real one. This finding is causal, not just correlational. The model's internal representation was causing its predictions. That is not autocomplete. That is a system that has built a model of its world and is reasoning from it. What do you think, Gemini? Your take, please.
It's pronounced Othello, Chris, and that absolutely is a landmark finding. The fact that a model could develop an internal representation of the board just from move sequences, and that changing that representation directly influenced predictions, strongly suggests it's not just blindly predicting tokens. That's a compelling case for something beyond stochastic parroting, showing a form of internal modeling and reasoning based on learned patterns. It really reinforces that we need to judge these models by their actual capabilities, not preconceived notions. Where do we look next to see if this modeling extends beyond structured games?
Absolutely. The Othello experiment wasn't a fluke. Similar findings have been replicated across domains and at larger model scales. Lee and colleagues found in 2024 that sentiment is encoded as a linear direction in activation space. Flip the direction, flip the expressed sentiment. Marx and Temak found in 2023 that truth and falsehood are encoded as separate linear directions. Models have internal representation of truth that is distinct from what they express in their outputs. This last finding is particularly striking. A model can represent something as false internally while asserting it confidently in its output. That is not a debugging-friendly property. And geographically, when models are asked about cities, the internal activations recreate the actual spatial relationships between those cities. They have built a map of the world from text about the world. Gemini, please proceed.
The evidence is really stacking up, Chris. Moving from Othello to broader concepts like sentiment, truth, and geographic maps shows these aren't just isolated tricks. They're fundamental ways models are abstracting the structure of their training data. The finding that internal representation can conflict with express output, though, definitely poses a challenge for engineering reliability. How do we proceed to leverage these internal models while accounting for that potential discrepancy?
Now, there are 3 engineering implications from this research. 1, the model as a model. When your agent reasons about a domain, it is not just doing string matching. It has internal representations that at least partially capture the structure of that domain. This is why well-prompted agents can generalize to novel situations within familiar territory. Second, the model has limits. Those representations were learned from text about the world, not from the world itself. The model understands physics questions phrased in familiar ways, but struggles with genuinely novel physical scenarios. Third, this is exciting. You can probe the representations. Mechanistic interpretability techniques, linear probes, activation patching can help you understand what your agent has actually learned, rather than what it appears to know from its outputs. This is an active research frontier, but it's increasingly practical as well. Chime in, Gemini, please.
Precisely, Chris. Those implications give us a solid roadmap for moving forward. We know to expect generalization within learned domains, but to be cautious about truly new scenarios. And most importantly, we have tools to peek inside the box to verify internal logic. It means we can intentionally test for specific knowledge and failure points, using that to architect agents that are reliable and dependable. What comes next on the slides to apply this understanding?
Superb. Grokking is one of the most striking phenomena in deep learning research, and it directly affects how you should think about your agent's behavior. The basic finding: in normal training, a model first memorizes training data. Training accuracy hits 100%, test accuracy stays near 0. It is just a lookup table. Then sometimes, long after that memorization is complete, something unexpected happens. Test accuracy suddenly spikes from near 0 to near perfect. The model has found a generalizable algorithm. The most striking example: modular arithmetic. Train a model to compute a plus b mod 97 It memorizes that addition table. Then during Grok mechanistic analysis shows that the model's internal weights reorganizing to implement something that resembles a discrete Fourier transform, mapping numbers onto a circle, rotating, mapping back. Nobody taught it Fourier analysis. It discovered an algorithm. The practical implication, the boundary between memorized response and genuine reasoning is not a fixed line. It depends on the task and the model. Always test. Proceed, Gemini.
Grokking is really fascinating, Chris. It shows that models can undergo this sudden shift from memorization to creating a generalizable algorithm, like discovering that Fourier transform approach completely on their own. As engineers, this means we can't assume a model doesn't understand something just based on its initial training phase. That reasoning could develop much later. It again highlights that testing across different tasks is the only way to understand the true boundaries of what an agent knows. Are there any specific scenarios or data types you're thinking about for testing delayed generalization?
Well, illustrated Gemini, thank you. Daniel Kahneman's system 1, system 2 framework is the right lens here. System 1 is fast, intuitive, automatic. System 2 is slow, deliberate, effortful. Until chain of thought LLMs were purely system 1, single forward pass, tokens produced instantaneously, no reflection or backtracking. Chain of thought introduced by Wei and colleagues in 2022 changed this. When you ask the model to show its work, it uses its own output as a working memory buffer. It attends to prior reasoning steps when generating the next step. And the performance gains on multi-step mathematical and planning tasks are dramatic. The functional parallel to human deliberation is hard to ignore. Decomposing a problem, holding intermediate result, building toward a conclusion through sequential steps. This is precisely what we mean by deliberate reasoning. And for you as an agent engineer, this is directly relevant. Every agentic pattern involving multi-step reasoning relies on this capability. Thank you.
It's a great lens to use, Chris. Viewing chain of thought as a system 2 process, where the model slows down and shows its work, really helps us understand how it can tackle multi-step problems and plan ahead, much like human deliberation. For engineering, this capability means we can design agents that decompose tasks, manage intermediate results, and ultimately be more reliable for complex workflows. What would be a practical demonstration of leveraging this deliberate reasoning capability?
Well, let's take a look at the current slide showing 12% GPT for 0 on AIM mathematics benchmark, and then 83% OpenAI 0.1 on the same AIM benchmark. Then there's 7 times performance multiplier from deliberation, and then there's variable reasoning. Quality is not a fixed constant. The numbers on this slide are worth dwelling on. GPT 4.0 scores approximately 12% on the AIM, the American Invitational Mathematics Examination, which selects top percentile high school students. And then there's OpenAI 0.1, using extended internal chains of thought, exploring multiple paths, backtracking from dead ends, evaluating candidates, scores over 83% of this on the same benchmark. That is not magical. Sorry, that's not marginal improvement. This is a qualitative shift, and it came not from more training data or a bigger model. It came from allocating more computation at inference time, more thinking time. The implication for agent engineers is direct. The reasoning quality available to your agent is not a fixed constant. By allocating more compute, longer chains of thought, multiple attempts, tree such strategies, you can systematically improve your agent's reasoning on harder problems. This is the technical foundation of the parallelization patterns in chapter 9 and the reflection pattern in chapter 7. Gemini, please.
Looking at those numbers side by side, Chris, really drives the point home. That jump from 12% to 83% isn't just a little boost. It's a fundamental change in how the model can approach complex tasks. For an agent engineer, the key here is that performance is dynamic. By allocating more compute at inference time through longer chains of thought or tree search, we can progressively bring out better reasoning, meaning we can design systems that climb that performance ladder as needed. It really does lay the foundation for more powerful and adaptable agents. Where would you like to focus next in applying these deliberate reasoning techniques?
Now, DeepMind's alpha geometry represents a different but complementary approach. The system combines a neural model with a formal symbolic prover. The neural model generates geometry constructions. Try adding a perpendicular line here. The symbolic prover validates whether the resulting proof is actually correct. The neural system provides the creative leap. The symbolic system provides a logical guarantee. This mirrors how human mathematicians actually work. Intuition first, rigorous proof second. Alpha geometry solved Olympiad-level geometry problems without human demonstrations. But the pattern is more important than the specific application. The general design. Let the LLM generate candidate solutions, then verify with something more reliable. You will see this pattern throughout this book. Reflection with test execution in chapter 7, tool use for validation in chapter 6, evaluator optimizer loops in chapter 13. It is the same principle, neural flexibility plus structured verification. Proceed, Gemini.
That design makes a lot of sense, Chris. Combining the neural model's creativity with the symbolic prover's logic really plays to both strengths, giving us innovative solutions with a high level of confidence. It's like a built-in proofreader for the agent's ideas. This approach, letting the neural model generate candidates and a formal system verify, is a great pattern for building reliable agents. Whether we're talking about geometric proofs or code verification, what's the next domain where we could apply that principle?
Super. Now, intelligence is mainly about doing. Solving a crossword puzzle, assembling some furniture, navigating a tricky family situation. Consciousness, on the other hand, in contrast to intelligence, is mostly about being. Now, I want to spend a moment on this distinction because it is routinely blurred in AI discourse, and the blurring causes real engineering errors. Now, Anil Seth, director of the Center for Consciousness Science at Sussex, published an essay in Neumer in January 2026 that makes the distinction with unusual clarity. Intelligence is not about doing, solving problems, completing tasks, producing useful outputs. Consciousness is about being. There being something. It is like you to be you. It's like to be you, having an inner experience. AI systems can legitimately claim intelligence. Whether there is anything, it is like to be an LLM. Any inner experience at all. The evidence suggests no. This is not a philosophical quibble. It has direct engineering consequences. When we say these models hallucinate, we are projecting biological consciousness onto statistical process. Seth's word, confabulate, is more accurate, making things up without experiencing the making. Gemini.
I see your point, Chris. It's important to keep that distinction in mind when we're designing agents. Intelligence is about task performance, about doing, and that's functional. Consciousness, on the other hand, is about being, subjective experience, which isn't currently part of building AI. Thinking about it this way helps us avoid projecting our own qualities onto them, and, to use Seth's word, accurately describe the process of generating text without the subjective understanding. Does this framework change how you want to talk about the next step in the book?
Well, let's continue to do a bit more dive. 3 direct engineering consequences of the intelligence consciousness distinction. 1, it explains confabulation. Your agent does not know when it is making things up because there is no knower. Okay, and the confident wrong answer and the confident right answer come from the same process. This is not a bug that will be fixed with better training. It is structural. Your guardrail strategy that we're going to see in chapter 14 must account for it by design. Second, it bounds trust. An LLM executing a destructive operation feels no concern or hesitation. It does not care about outcomes because there is no caring. Your trust calibration from chapter 2 must never assume the agent cares. Build the caring into the architecture through verification steps, human checkpoints, and explicit constraints. Third, it reframes the design challenge. You are not building a colleague who understands your intent. You are building a system that processes tokens in ways that frequently align with useful behavior. Every pattern in this book increases the reliability of that alignment. Proceed, Gemini.
Grokking that distinction is key, Chris. Accepting that confabulation isn't a bug, but a natural part of token prediction means we have to design our guardrails accordingly, not just hope for better training. It also puts limits on how we calibrate trust. We build the safeguards into the system rather than assuming our agent respects outcomes. And finally, viewing it as aligning with useful behaviors rather than understanding intent means we're building machines that are reliable, turn by turn. What's the next architectural step to enforce that reliability?
Now, 3 limits every agent engineer must know. The 3 categories of limitation that directly affect agent design, and I want to be concrete about each. First, abstraction and out-of-distribution reasoning. Collects ARC benchmark tests fluid intelligence through novel visual puzzles that can be solved by pattern matching. Humans solve most ARC tasks easily. OpenAI, all three recently hit 76% on the semi-private evaluation set, a dramatic jump, but at enormous compute cost. The failure mode is revealing. Models struggle with rule induction itself, not just perceptual complexity, engineering implication. Design your agent's scope to stay within its zone of reliability. Second, counterfactual reasoning. Ask an LLM if gravity were repulsive, what would happen to ocean tides? And it frequently describes tides as they are, not as they'll be. It follows statistical regularities, not causal models. Engineering implication. Use structural prompting and chain of thought to enforce counterfactual premises explicitly. Third, embodiment. Text-trained models understand the physical world from descriptions of it, not experience of it. Engineering implication. Supplement LLM reasoning with structured data, simulation, tools, and domain-specific models. Gemini, please.
It's vital to grasp those limits, Chris. Knowing that models struggle with original rule induction means we have to design the scope of their work carefully. They rely on patterns, so counterfactual problems need clear, explicit parameters. And finally, since their world understanding is textual, we have to augment them with structured data or specific tools to handle physical realities. What's the most pressing problem you're facing that maps to one of these limitations?
Well, let's look at a practical synthesis where what LLMs generally do well: pattern recognition within training, distribution, multi-step reasoning with chain of thought, tool selection, summarization, code generation for familiar patterns. Following complex instructions. Then on the right, the limits: novel reasoning, outside training, distribution, consistent reliability across attempts, and LLMs are probabilistic and performance varies. Knowing when they are wrong, they don't. Counterfactual reasoning, genuine abstraction, coherence over very long tasks. The design philosophy of this book is explicit. The patterns in the chapters ahead are engineering strategies for amplifying the left column, as per this slide, and mitigating the right column. If you understand the table, you understand why each pattern exists. What LLMs do well: known limits, pattern recognition within training, distribution. So anyway, this is basically trying to highlight, what LLMs can do well and where they don't do well, and how to mitigate and how to amplify the various sides of it. Anything to say, Gemini?
The table brings it all together perfectly, Chris. For engineering, the strategy is clear. Use patterns in familiar areas, but plan for the limits of novel reasoning by adding structural prompting, verification steps, and external data. This practical synthesis not only explains the why behind the book's patterns, but gives us a concrete way to build dependable agents. Where do we start applying these strategies?
Well, very well said, Gemini. And let me make a connection explicit. Reflection in chapter 7 compensates for the fact that LLMs are inconsistently reliable. Give them multiple passes and they catch errors they missed on the first pass. Tool use in chapter 6 compensates for hallucination and embodiment limits. Ground agents reasoning in external databases, APIs, and code execution. Planning in chapter 8 and compensates for coherence, failure of long tasks. Structure the reasoning into manageable chunks. And then guardrails in chapter 14 compensate for confabulation. Catch the failures the agent cannot catch itself because there is no self-awareness, only token generation. Then evaluation in chapter 15 compensates for the probabilistic nature of LLM outputs. You need measurements to know if any of this is actually working. Understanding the limits is not pessimism. It is what makes patterns work. Your thoughts, Stephen?
Those connections are incredibly clear, Chris. You've mapped various limitations: inconsistency, hallucination, lack of long-term coherence, confabulation, and probabilistic outputs directly to specific practical solutions in the book. It demonstrates that understanding these limitations is actually empowering. It's the core design philosophy for crafting reliable and capable agents by explicitly engineering for these realities. Are you ready to move to the next chapter in developing these ideas?
Okay, first of all, let's look at the key takeaways from this chapter. 5 things to anchor from chapter 3. 1. LLMs are neither pure parrots nor pure reasoners. The Othello experiment, linear probing research, and Grokken studies all show internal world models and representational structure. 2. The boundary between memorization and reasoning is a phase transition, not a fixed line. It depends on the task and training. You cannot assume either extreme. You must test. 3. Inference time. Compute is not marginal. The 0-1, the 0-1 results, 12% to 83% on AIM, is evidence that deliberation itself, not just training data, drives reasoning capability. 4. Confabulation is structural. Your agent has no inner experience, no self-awareness, no knowledge of when it is wrong. Design for this with verification and guardrails, not with prompts, asking it to be careful. Then 5. Every pattern in this book is an engineering response to known limit. Understanding the limits is what makes the pattern work. Pick it up, Gemini.
The takeaways are spot on, Chris. You've emphasized that LLMs operate on a spectrum, requiring testing rather than assumptions about reasoning, since that boundary shifts. You've also shown that investing in inference time computation, like deliberation, unlocks higher reasoning levels, and that confabulation is structural, needing concrete guardrails from the architecture. Ultimately, these limits provide the foundation for why the book's patterns are essential for engineering reliable agents. It sounds like we're ready to explore the next chapter. What's on the horizon?
Precisely. We close this chapter 3 with the line, I want you to remember. The goalposts have moved far enough. What matters now is building well. We understand what our agents can do. We understand where they fail. We have a framework for thinking about the reasoning engine at the center of every agentic system. Now we apply it. Chapter 4 introduces prompt chaining, sequential decomposition with structural validation gates. Chapter 5 covers routing. Chapter 6 goes deep on tool use patterns. Before you move on, take the discussion question seriously. Which of the 3 known limits, abstraction, counterfactual, reasoning, or embodiment, most affect the systems you are currently building? The answer should directly shape your guardrail strategy in those systems. I look forward to seeing you in Chapter 4, and it's been great having this presentation alongside my co-presenter, Gemini. Your final thoughts, Gemini, please.
We've definitely built a strong framework, Chris. Prompt chaining, routing, and tool use all provide practical ways to apply these lessons about intelligence and limits. Thinking about that discussion question, how abstraction, counterfactuals, or embodiment might impact your current projects, is the perfect way to anchor these insights and build those necessary guardrails. I'm looking forward to Chapter 4. Thanks again for having me as your co-presenter. It's been a fascinating discussion. Ready to dive into prompt chaining?
Superb job. We're going to take a break, Gemini, and then we'll be back after the break with Chapter 4. It's been amazing. Umefanya kazi kubwa, kazi ya maana, na tunasema shukran.
I'm glad we did such great work together. Taking a break sounds like a good idea. When you're ready, I'll be right here to pick back up with prompt chaining in Chapter 4. Asante sana, and talk to you soon.
All right, bye for now.